Hey everybody, welcome to video 3 of lecture module 6, where we're going to take a look at the surface of Venus and its interior structure and its lack of a magnetic field. Let's go ahead and jump right in with a preview of what we're going to be talking about. There we are. So we're going to talk about the surface of Venus. We're going to look at its two continents, what we call the Ishtar Terra and Aphrodite Terra. We're going to take a look at all the volcanic evidence that we have of Venus, try to figure out whether or not Venus has plate tectonics. Spoiler, it doesn't. We'll take a look at its shield volcanoes and other volcanic features, specifically its lava domes and these unique to Venus features called coronae. And we'll even go into this wild idea that maybe Venus was or is just a giant supervolcano waiting to erupt again. And then we'll go ahead and talk about the fact that it doesn't have a magnetic field, it's too slow to dynamo, and the interior structure of Venus for the best that we know it. So launching right in, we have already taken a look at a global view of Venus, and we were unable to see the surface in visible light. However, we can leverage different parts of the electromagnetic spectrum, especially long wavelength infrared and really especially radio wavelengths that can peer directly through the atmosphere and give us a map of the surface. So we can use longer wavelength radio waves and get a map of the surface like this one right here that's from the Magellan mission from NASA. And this gives us our first view of the surface of Venus. And things that you can take note of, what are our major terrains, is that you'll notice that we have these brighter, higher elevation surfaces. And here's one over here, and you'll have some up there as well. And we can see that in general, there are two very, very large plateaus. Continent-sized highlands is maybe a better way to put it. And we call them the Ishtar Terra and the Aphrodite Terra, two of my favorite names of all the surface features that we talk about in this class. What about the rest of the surface, all this darker stuff down here? In radio, darker means smoother, so we're looking at the lowlands. They're lower in altitude. They are smooth. They don't have very many craters on them at all, which I'll come back to here in a second. And you would describe it as lowlands that are flat and have some rolling hills. There are also the rocks there are volcanic in nature, some evidence that we're going to look at as well. And you can do some crater counting. And if you look at these areas, you'll notice that the surface of Venus, pretty much everywhere, is remarkably young. It dates from about 300 to about 600 million years, a nice little bracket. Right there, you can just think, and I'll continue to refer to this as 500 million year old surface. And that's the entirety of the surface, almost as if something happened 500 million years ago that resurfaced the entire planet, because it's so consistent everywhere we look. So let's talk about the major terrains. Let's talk about these two continents, these high elevation plateaus. Now, before I start talking about any of the text that's over there, I want you to go ahead and take a look at these, and I want to be very, very clear that the blue here is not water. It's just coloration of topography. Why the makers decided to color the low stuff blue when they knew it would be confusing with oceans, I'm not quite sure. So right down here, we are looking at a Mercator projection of Venus. And you can see a couple of things right there. One of the first ones I'd like you to remind you about, hang on while I move some stuff around my screen so I can see what I'm pointing at, is that we have the south on the top and the north on the bottom. And that's because, if you remember, Venus is tipped upside down, giving it its retrograde rotation. And then you can do a comparison to Earth and Venus up here, just other Mercator projections, and you can even see the plate boundaries on some of this with Earth. You don't see any of that evidence on Venus, but you do have these two highland areas. Here on the South Pole, remember, this south is up because Venus is upside down here. You have the Ishtar Terra. Land size-wise, it's about the same size as Australia. So pretty big. It's a continent-sized object. And here we have the Aphrodite Terra here on the equator. I know it looks smaller here, but that's because Mercator projections accentuate the poles. The Aphrodite Terra here in the equatorial regions is about the same size as the entire continent of Africa. So both of them are continent sized, and they take up about 8% of all the Venusian surface. The other 92%, or the majority of it, are these lowlands. You have a couple other highland hot pockets but for the vast majority, the rest of it are these lowlands. I want to go ahead and take another view of this. So this is using different data where you can actually see this on sort of a global projection. So here you can see one of the edges of Aphrodite Terra, and the other half would be on the backside of the planet, which we can't see. And this is from Magellan, so it's a little bit better data than the Pioneer data. And you can see the rest of it. And here you can see that Aphrodite Terra is quite large, much, much, much larger than the Ishtar Terra. And why can we see this? It's because we have to use radio waves, just good stuff to know for upcoming exams. I want to go ahead and take a look at volcanism and the volcanic features on Venus. This is going to be one of the more interesting pieces of the history of Venus. It's going to help us solve this puzzle of the surface being only 500 million years old. And if you think about it, Venus is almost the same size as the Earth, 95% the size, 81.5% the mass. It's made out of the same stuff, has the same composition, has the same uncompressed density, therefore it should have the same composition, should have the same interior structure as the Earth, and it should have the same level of volcanism as the Earth. But we maybe, just maybe, see active volcanism. If you want to know more on whether we see active volcanism on Venus and the evidence for it, see the supplemental slides. We do see, however, evidence that Venus was quite recently, 500 million years or so or less, quite volcanic. And maybe the easiest way to link our volcanism on Venus is actually take a look at its volcanoes. So if you look over the entire surface of Venus, we've counted up 167 volcanoes that from one side to the other have diameters of 100 kilometers or larger. Here's a 300 kilometer scale bar, so this one's coming in at about 600 kilometers in diameter. This is Sif Mons and Gullah Mons, two of these shield volcanoes. So shield volcanoes are the type of volcano that are not related to plate tectonics. So every volcano in the solar system that's not on Earth, since no other planet has plate tectonics, are shield volcanoes. They have a low profile, which means they rise slowly, and then they'll have a caldera, a crater, a volcano crater at the top, and they all have that sort of shape. A good example of a shield volcano would be the Hawaiian Islands here on Earth. However, unlike the ones on Earth, the volcanoes, the shield volcanoes on Venus, are about 10 times larger on average than your Earth shield volcanoes. So they're enormous volcanoes. It probably has to relate to the fact that there is no plate tectonics on Venus. So what other evidence of volcanism do we see on Venus other than the shield volcanoes? We see lots of lava flows. Here's a lava flow down here. Again, radar, brighter colors mean rougher surface. So this dark area right here is a very, very smooth surface. If you look at the supplemental slides, it zooms in on this. You can see a fissure where lava flowed up, filled in the land right here, and has made a very smooth volcanic plain right there. So we see lots of these lava flow features. So clearly there's been a good bit of volcanism on Venus. Notice you don't see any craters, so they're quite young. And it comes out to be about 500 million years old. Some of them, like these volcanic flows, are slightly younger. There might still be active volcanism on Venus. We're also going to look at lava domes, not unique to the planet Venus. We see lava domes on all planetary surfaces. So these are not unique to Venus. But on Venus, they have a very, very specific shape or appearance in the radar that make them look like pancakes. So we like to refer to the lava domes on Venus as pancake domes. These are not unique to Venus. What is unique to Venus are these large-scale volcanic features, tectonic features, called coronae. Let's take a look first at the lava domes that are aptly named pancake domes on Venus. So here you can see a series of them. They often appear clustered together. The scale bar here is 40 kilometers, so these are about 20 or 30 kilometers across. But typically, that's a little bit on the larger end. They can appear 1 to 15 kilometers in size or so, or a little bit larger. And these are simply lava domes. You see them on pretty much every planetary surface that has a surface. And the way that they form is that you're going to have lava that can come out onto the surface. The lava is going to be thinner. It's going to have lower viscosity. So it forms this very low profile dome. And then after the magma in the chamber retreats, you have a bunch of empty space right there, and gravity causes it to collapse down, forming this sort of flat topped round feature, which when looking in the radar, you can see all the fractures look like pancakes on Venus. So here we have our pancake domes. They're usually associated next to the unique to Venus feature, the coronae, which are much, much, much larger and also related to volcanic or at least magmatic features. So just to really point out, these are not unique to Venus. What is unique to Venus are these monstrous features on the surface of Venus called coronae, singular corona, which is the Latin word for crown. So no, this is not a reference to the beer, although if you look at a bottle of Corona, the symbol is a crown. So it's a reference to the crown-like appearance that these coronae have. And these things are scattered all over the surface of Venus, and they are absolutely huge. They are hundreds to thousands of kilometers across. Our scale bar is 500 kilometers here. This thing's nearly 1,000 kilometers in diameter. So how are these thought to have formed? Venus does not have plate tectonics, but it still has a lot of the same mantle features that Earth does. Probably a lot of it's still molten. You have convection going on there. You're going to get hot spots. You might get this very, very large hot spot, which is going to push up on the crust, causing it to bump up like a pimple on the surface. And then as that magma retreats, then it would relax back down. And whenever it relaxes back down, you get these ring-like fractures right here that outline the corona. And the fact that this was associated with a magmatic hotspot, no surprise that you're going to see fissures, volcanic fissures, these fractures here, and you're going to see all these lava domes that, yes, they do look like pancakes on Venus. So these are spread all over the surface of Venus, these coronae, and they are unique. We do not see these on any other planet's surface. So these are unique to Venus. Let's go ahead and hammer in this fact that Venus does not have any evidence of plate tectonics. Whenever we looked at a map of Earth's volcanoes or where they occur and where its earthquakes occur, we saw that they clustered around the plate boundaries. So if there is a clear clustering, a clear pattern to where volcanoes and volcanic related features appear, that is evidence for plate tectonics. Let's look at where the shield volcanoes, the coronae, and just calderas are on Venus. They are scattered all about the surface of Venus. So here's this is a north-south latitude versus longitude. And you can see they're scattered all about. There's no rhyme or reason. They're not clustering around plate boundaries, which means that it doesn't really have plate tectonics. Venus's crust is a nice solid crust, where Earth's crust is broken up into the tectonic plates. So no plate tectonics for Venus. What is the surface like? How do we know that the surface is volcanic? Well, we know it's young and not very much else can resurface, but we know that it's volcanic because the USSR sent 16 probes to Venus called the Venera probes. 10 out of the 16 of them survived their descent through the thick atmosphere, landed on the surface. Now, given that the surface is hot enough to melt lead, they had a very short shelf life before everything just sort of melted and broke. And Venera 9 lasted the longest, the only one for a significant amount of time, 53 minutes. The other 9 didn't survive very long at all. Here is actually a view, and it's been colorized to what it would look like, or suspected to look like if you were on the surface. Here's the edge of the probe, one of its landing legs. And you can see out on these volcanic plains. And it's very dark in color, low albedo. These rocks are basaltic rocks. They are lava that has solidified. So these are volcanic in origin. Almost all the rocks that the Venera probe saw were volcanic in origin, although they did see some granitic crustal material. So the vast majority of the surface has been resurfaced via volcanism. And by crater counting, we know that happened in about the past 500 million years or so. There hasn't been a resurfacing event since then, since all of Venus's surface is about 300 to 500 million years old. Now we can put the pieces of evidence together to perhaps one of the most fascinating ideas in our entire solar system. So we have the Venusian surface that is young and volcanic. The entire surface is about 500 million years old. We see no evidence of plate tectonics, and we know from the Venera landers that the surface is volcanic rocks. So something 500 million years ago happened on Venus that resurfaced pretty much the entire planet. The other thing we need to think about is Venus is Earth's twin planet. It has, being pretty much the same size baked potato, and made out of the same stuff, it should have mostly the same things going on with it, minus the plate tectonics. So it should have the same amount of overall volcanism as the Earth does. But without these the tectonic plates that are fracturing the crust acting as a pressure relief valve, so like a pressure release on a pressure cooker, Venus has one whole solid surface. It is a pressure cooker with no emergency release of pressure. Should have the same amount of volcanism, so over time, all that pressure of that volcanism that wants out is pushing out onto Venus, and it's hypothesized that every 500 million years or so, there's some global catastrophic event where that pressure finally wins out, and it's like with a pressure cooker that doesn't have a release valve, eventually that thing's going to explode, except Venus isn't going to blow up as a planet. The entire surface is suspected to erupt in one giant volcanic eruption, a planet-wide supervolcano. Kind of like Yellowstone is a supervolcano, but the entire planet of Venus. That releases the pressure, allows a method to resurface all of Venus all at once, and then the pressure would start to build back up. So this is suspected to occur every 500 million years or so. All right. Now let's take a look at the interior structure and the lack of the magnetic field for Venus. So if we want to talk about if Venus has a magnetic field, we should go through our planetary dynamo checklist. Is it a big enough baked potato? 81.5% the mass of the Earth, 95% the radius, check. So yes, it should have a liquid metallic outer layer. The other thing that we have to look at, the rotation period. Does it rotate fast enough to drive the dynamo? Well, its rotation period is 243 days. The limit that I had put is 50 days. This is about 5 times longer. This is way too slow to dynamo. So it's expected, and we do not detect a global magnetic field. So Venus does not have a global magnetic field. What about the interior structure? We don't have any seismic data, and we don't have very much data on how, looking at its gravity maps, trying to get those moment of inertia, comparing how it rotates to its gravitational field. So we really don't have any solid information on the interior structure of Venus. However, Venus is roughly the same size as the Earth, made out of the same materials of the Earth. So we can reason it out based on what's called comparative planetology, that Venus's internal structure should be very much like Earth. It should have an iron core, a rocky mantle, and a low-density rocky crust, probably of roughly the same thicknesses, maybe a little bit of a thicker crust since it doesn't have plate tectonics. But that is about all we can say about Venus's interior for the moment. Hopefully we're going to be learning more as we get more and more data, especially from the Japanese Akutsuki, mission, also called the Planet C mission. So hopefully we will have more about that soon. And that ends my discussion on the interior structure and the surface of Venus. I will see you where we get to talk about the atmosphere of Venus, which is one hellish place to be.